Monte Carlo simulation is one of my favorite tools in business analytics because it allows us to answer questions about probabilities without really having to do any math, any sort of counting. We're only limited by our imagination and our computer programming skills. So, what is Monte Carlo simulation and where do we use it in business analytics? Now, it ties into what we learned in Unit 1 about the probability of an event and how that's defined from the frequentist view. So the frequentist view says that the probability of some event is just the long-run fraction of time where that event occurs, assuming we're talking about repeated trials, all conducted under identical conditions. So if I want to know the probability of my travel time being less than 15 minutes when I go to work, what I can do is I can just day after day after day after day, basically day as a trial, count up the number of days where my travel time was indeed less than 15 minutes. And the frequentist view says that in the long run, that fraction, the number of days where my commute time was less than 15 minutes, divided by the total number of trials I've conducted so far, that's going to be pretty close to the probability of that event occurring. And we talked about in Unit 1 special ways where we can go and calculate the exact probability that an event occurs without actually conducting any sort of trial. We learned counting, we learned combinatorics, we talked about the birthday problem. And we could get at probabilities that way, but sometimes the math was just a little bit too difficult. If you think back to the birthday problem, we wanted to know what's the probability that at least two people in a room of 45 students are going to share the same birthday. And what we had to do to come up with an answer was to be a little bit rude about it and to ignore all of the people born on February 29th, just so that the math came out easier. Now, Monte Carlo simulation is going to help us answer these probability questions with a different approach. What we're going to do is to write a computer program that's going to go and conduct a trial for us. We're going to write some computer code that determines whether or not our event of interest occurred, like two people sharing the same birthday, and we'll have the computer just run trial after trial after trial after trial. And after a sufficient number of trials, that fraction, the number of trials in which that event occurs, divided by the number of trials we've run, that's going to be a pretty good estimate of the probability of our event of interest. So you can see some of the power of Monte Carlo simulation in business analytics. One of the classes you might take as part of the master's program in business analytics is a class on simulation, discrete event simulation. So you might set up a computer program that provides a fairly realistic model of a factory floor. Maybe this factory floor is in charge of testing engines, and you want to study the probability that at least 3 engines per hour are going to be able to be inspected, repaired, etc., based on a certain factory layout or a certain staffing schedule. So how can you possibly even answer that by, doing counting, doing math? You might be able to come up with a guess if you just look to see at the results from hour to hour, from day to day, etc., but that's very time consuming. What if you could write a computer program that mimicked what the factory floor looked like, mimicked the processes of doing testing, doing repair, the engines being delivered and kind of shipped out, etc. If you could just have the computer program go through 10 years of what's going on the factory floor, you could very quickly come up with these probabilities. The probability that at least 3 engines would be able to make it out of the facility in an hour. Or if you're into finance and you're interested in doing investments, you might like to know, well, what's the optimal strategy for asset allocation? You can buy some stocks, you can buy some bonds, other commodities, and you might like to know, well, what's going to be the best set of things to invest in together in order to maximize my profit and to minimize the risk. So one thing that you could do is to try out various strategies. And if you had a fairly realistic simulation about the price evolution of these stocks, these bonds, these commodities, you could come up with a pretty good idea for what might happen in the future. The probability that the return on investment was, say, at least 20% or 50%. And you could go through and walk through a bunch of different random scenarios to see how different investment strategies stacked up with each other to come up with your ultimate investment strategy. Likewise, if you're working for Kroger, maybe you're thinking over, well, what if we redesigned the entire store layout? That's going to affect the way that shoppers move through the stores. Different items placed against each other might change people's shopping behaviors as well. We'll talk about market basket analysis in this course and in other courses. And so the decisions you make about where things are located in a store, how the store layout is going to affect the bottom line. How can you possibly figure out, okay, well, changing the store layout, what's the probability that it increases, say the amount of money people are spending by 5%? How can you get that probability? Well, even running a trial might be a little bit too difficult. But what if you had a pretty good understanding of customer behavior, where customers go around in the store? Well, maybe you could set up a computer to run through various scenarios, inject a little bit of randomness just so that each simulation is different from one trial to another, and come up with a pretty good comment about what might happen if the store layout changed. Likewise, you could test to see, well, what would happen if we set out different customers, different sets of coupons, promotions. If you have a realistic simulator, you can start having the computer just conduct a ton of different trials. And from that frequentist view of probability, once you calculate the fraction of trials where your event of interest occurs, for a sufficient number of trials, you've come pretty darn close to estimating that probability. And so that's what we want to do in this unit. We want to learn how can we write efficient computer programs to help us estimate probabilities. And we'll take that even a step farther. We'll actually just use Monte Carlo simulation to study the outcomes to some random process. And in fact, if I got to choose any superpower out there, flying, invisibility, teleportation, going back in time, I would actually choose something that's really closely related to Monte Carlo simulation. Because most of the time, if I'm just sitting around daydreaming, I'm thinking of questions that have numerical answers. So, I love my Frenchies, Cannon the brown one, Jackson the white one. I would love to know, well, how many other people in the world also have a pair of Frenchies, one who's white and one who's brown? Or maybe I'm flying to the West Coast to visit my family, and I might look out the window, look down at the ground and say, I wonder how many of those people are learning about analytics right now, or sleeping, or driving a car. I'd love to know that answer. Or I might be rocking out to kind of an obscure song by The Cure, a band that I really liked as I was growing up, and I might wonder, how many people are listening to this song right now? A lot of things that I wonder about have numerical answers, so if I could choose a superpower, I think I would choose to just know the answer to any question that had a numerical answer. I think that would be cool. And maybe also if I could, add in a little bonus superpower there, I'd love to be able to glimpse into alternative universes, kind of like Doctor Strange, just to see how things could have turned out differently if a different set of decisions were made. So if I turned left versus turned right, would that have changed the travel time to work? And that's what Monte Carlo simulation allows us to do. It allows us to explore all of these alternative universes where things turn out slightly differently by intelligently injecting a little bit of randomness to help us answer questions not only about probabilities, but also just study in general what various aspects of a process might look like as things unfold. So how are we going to do this? What's going to be the radioactive spider that gives us this superpower to glimpse into alternative universes, to see how the outcome of some random process might change? Well, the answer is to do some programming. So you guys took the R exam over the course of the summer, and a big part of that R exam was setting up the skills that are required in order to pull off a quick and efficient and meaningful Monte Carlo simulation. So the nice news is that Monte Carlo simulations all have the same very basic shell, because a Monte Carlo simulation doesn't have to do too much. It just has to go and simulate some random process, measure the outcome, and then figure out if the outcome of interest occurred. And in fact, the most basic Monte Carlo shells all look like this. We decide ahead of time, hey, how many trials do we want to go through? And so I might left arrow a variable called n trials to be 10,000 or 100 or 1,000,000, depending on what my time budget is. And then I'm going to pretend to basically do those trials by hand, but actually have R conduct all of the heavy lifting. So because the frequent diffuse says, well, count up the number of times you've seen your event of interest occur, let's go ahead and define a variable called counter to start out at the number 0. We haven't seen the event yet. Counter is going to keep track of how many times we've seen that event. It starts at 0. And then what we'll do is we'll use a control structure, a for loop in R, to perform these repeated trials. This will be the engine of the Monte Carlo simulation. This is what we'll set up in order for the computer to run trial after trial after trial. Now, the hardest part of the Monte Carlo simulation is getting the logic of how a trial is actually executed correctly. So the code that actually performs a trial might be really quite involved. It could be really simple, like flipping a coin, seeing if it's heads or tails, rolling a die, see if it's 1 through 6, or it could be something very complex, like simulating the random demand over the course of a month of 50 different products, and then looking to see, well, how many of them had a stock out. So sometimes we might have hundreds of lines of code that go inside a for loop that help us conduct a trial. But once the trial has been conducted, the next part of the Monte Carlo simulation is involving some sort of if statement, some conditional programming, to check to see if your event of interest occurred. And then if it did, well, we know we're supposed to keep track of the number of times it occurred. We're going to take the value of counter, that variable that we've designed that's counting up the number of times we've seen that event. We'll add 1 to it and then left arrow it back into counter to overwrite its previous value. Once the for loop is concluded, well, the value, counter divided by n trials, will give us the fraction of trials where we saw that event of interest occurred, and that's going to be a pretty good guess of the probability of that event. In fact, spoiler alert, we're going to know how close our estimated probability is to the true value of the probability by looking at the margin of error of the estimate. So by throwing p hat, our estimated probability, into this equation, we'll have an idea if our estimate is good to plus or minus 5%, 1%, 0.3%, etc. A lot more on that later when we start talking about confidence intervals, but for right now, be assured that after you've run your simulation a certain number of trials, you're going to know roughly how close your estimate is to the truth. Now, because the engine of a Monte Carlo simulation is this for loop, it's worth reviewing how a for loop works. And I like thinking of it in 2 different ways. If I were to throw a for loop at you, what is the underlying code that gets run as the for loop is being executed? So translating it from the for loop to, the baselines of code, and then also vice versa. If I had a big chunk of code and I wanted to make that efficient by writing a for loop to execute it, how could I do that? How could I compress a big chunk of code into just a for loop? So let me go through an example both ways, and if you're experts at for loops, go ahead and just skip this part, but if you need a bit of a review, I think this will be quite helpful. So let's start out by just throwing a for loop at you and talking about, well, what's going on behind the scenes? The for loop is the engine of the Monte Carlo simulation. It's a shorthand for running hundreds, if not millions of lines of code. So how does it work? What does R do when it runs into one of these control structures? And so here's going to be my example. I have some code that initially left arrows a variable 5 to equal the number, variable x to equal the number 5, and then some sort of for loop is executed. So what goes on behind the scenes when R executes a for loop? Well, let's just kind of unwind this for loop and write out the component lines of code. So what happens when R sees the keyword for? Well, the first thing that it does is it looks for the parentheses associated with that for loop and dives into those parentheses to identify the relevant components. You're always going to have that keyword in, and what R will do is it'll check to see, well, what's on the left-hand side of in and what's going to be on the right-hand side of in. And so when R starts running this for loop, what it is going to do is it's going to define a variable, the name of which is whatever is to the left-hand side of the in, and its initial value is going to be whatever is in the first element of whatever happens to be the right-hand side of in. We're going to call the object on the left-hand side the looping variable, and the object on the right-hand side the looping vector. What R is going to do as it sees that for loop for the first time, it's going to define that looping variable to be the first element of that looping vector. So for this example, the name of our looping variable is I. The first thing R is going to do is it's going to essentially run behind the scenes the command I left arrow, whatever the first element of that looping vector is. So I know just by looking at it that that's equal to 4, but to make that absolutely clear, I'm going to write out that looping vector and just slap a bracket 1 at the end to signify that the first time through the loop, it's going to be the first element of that looping vector. So let's look to see what's happening. X is equal to 5. I is going to be equal to the number 4, the first element of that looping vector. And then what R does is it simply copy-pastes and runs all the lines of code that are inside the curly brackets. So in this case, it's taking the current value of X, adding 2 times the current value of X, then adding 5, and then left arrowing the result back into X, essentially overriding its previous value. So right now, X is 5. If I take 5, add 10 to it, and add another 5, that should be 20. So I should see X to be equal to 20 here. We've run out of code in the curly brackets, so when that happens, what R does is it goes back to the parentheses associated with that for loop, and it is going to redefine the value of that looping variable. So now I is going to be left arrowed to the second element of the looping vector. Second time through the loop, second element of that looping vector. So to make that absolutely clear, I'm just going to slap a bracket 2 after our looping vector to show you that I is now going to be equal to 8, that second element. It's going to copy-paste the code inside the curly brackets, run that. X is equal to 20, so it'll take 20, add that to 40, that's 60. Add 5 to it, 65. We should see X being equal to 65. Runs out of code, goes back to the parentheses. It's going to redefine the value of the looping variable I. We've named it I. Left arrow, the third element now of our looping vector. It's going to be 10. I is 10. And it's going to run the code inside the curly brackets. So X is equal to 65. 65 plus 2 times 65, I think that's 195. Add 5 to it, we get 100 or 200. Boom. Quick math in the head. So this for loop is really just shorthand for this set of code. And you can see that if our looping vector had a lot of elements to it, this is going to be a huge time saver. We don't have to have multiple lines of code spanning many, many different pages to accomplish something fairly simple. So that's one skill you're going to want to keep with you, is translating from a for loop into the code that's running behind the scenes. Just think like R and just walk through what exactly R is doing at each moment in that for loop. Now, the other way you want to think about this is that if you do run into some situation where you could save a lot of time or a lot of kind of coding, typing here, by writing a for loop, how do you actually go about doing that? And to illustrate this, what I'm going to do, delete all that hard-earned work. I would like to write a for loop that produces the following sequence. So the sequence is going to start out at a particular value, let's say 0.7 here. And what I would like to do is I would like to make X a vector. And what I would like is for the next element of that vector to equal 3.6 times the current element times 1 minus the value of the current element. So right now X is 0.7. The next value of X, the second element here, would be 3.6 times the current value, 0.7. I'm going to write that as X bracket 1. That's kind of what it's starting out as. 1 minus X bracket 1. All right, so that will be the second element. The third element is going to be defined in terms of the second element here, the one that comes before it. And so in theory, I can copy paste this code, make the relevant changes, hope I don't do any typos, and make this vector X as long as I really want it. But that's pretty inefficient. I've defined the first 5 elements of X right here. That wasn't really too bad, exercising a lot of care. But what if I wanted to make the vector X 50 elements, 100 elements, 1,000,000 elements? Well, I'm not going to write each line of code individually. This is definitely going to be a job for a for loop. Now, how do I know it's a job for a for loop? Essentially, each one of these lines of code looks the same. There's only one thing that's really changing from one line to another, and that's the number that I find inside the square brackets. It's going up in a regular pattern, from 2 to 3 to 4 to 5. This is 1 to 2 to 3 to 4. And so when I can spot something like that, where I'm running a bunch of lines of code that essentially look the same except for one small tweak, that says, well, why don't I use a for loop to run all of those lines in a much more efficient manner? So how do I go about doing this? Well, if I'm going to write a for loop to do something, I actually start out most of the time just writing out the first few lines of what I want that for loop to do, and then set the for loop up. Identify the name of the looping variable that I want it to be, and then also the looping vector, and figure out what the code needs to be inside the curly brackets. So how can I translate this into a for loop? Well, I'm going to start out by writing just all for loop skeletons. So we have the keyword for, we have the parenthesis, we have in the middle of the parentheses, and we have some curly brackets. And I'm going to fill these in one by one. Now, the first thing I'm going to do is to fill in the looping vector, the values that I'm looping over. So in this case, I can see I'm looping over the values 2, 3, 4, and 5. I'm doing something when the line has 2 there, 3 there, 4 there, 5 there, maybe 100, maybe up to 5,000, however large I go. So in this case, I'm interested in looping over the values 2 through 5, the integer sequence 2, 3, 4, 5. So right-hand side of the in, that's going to be where my looping vector is. That's what I'm looping over, in this case, the integers 2 through 5. On the left-hand side of the in, super easy. That's just going to be the name of the looping variable we're going to use as a placeholder in our code. Now, the name of the looping variable, completely up to you. Very often, if I'm looping over integers, I'll just use the letter I to be my looping variable. But being as clear and explicit as you possibly can is typically a good idea, just to make your code as readable as possible. So what I'm going to do is I'm going to use as the name of my looping variable the word index. Index kind of lets you know where you are inside of a vector, which element you're referring to. And so let's go ahead and write our for loop in terms of the looping variable index. So what do I want the for loop to do? Well, I essentially want to run this line of code, just dynamically figuring out, well, what's going to be the value inside these square brackets. That's the only thing that's changing from one line to another. So what I'm going to do is just copy one of these lines of code. These all look basically the same, and I'm going to figure out how to adapt that line so that it plays well with the for loop structure. So what do I want to do? Well, in this case, I know the value of index here. It's going to start out at 2 the first time through the loop, then it's go to 3, then 4, then 5. I can go ahead and just replace this 4 with index. The first time through the loop, index will equal to 2, just like this line. The second time through the for loop, index will be equal to 3, the second element here. I'll essentially reproduce this part. So all I need to do is tweak, well, what's inside the curly or the square brackets on the right-hand side of that left arrow. And it's always just index minus 1. So if I see a 3 on the left, I see a 2 on the right. If I see a 5 on the left, I see a 4 on the right. Index minus 1 will make that reference correct universally. And so there we go. That's going to be my for loop. The only thing I need to make sure is that I've initialized x to be a value. I'm not allowed to actually put stuff into a vector with square brackets until that vector exists in the global environment. So sometimes I'll start it out with a blank vector. There's nothing in there. In this case, since I'm starting it out with the number 0.7, I'll start it out at 0.7 and I'll let the for loop run. And I see at the end of the for loop, I get the same set of values as I did when I was doing it manually. So untranslating, I guess we would say, okay, x starts out at 0.7. As r dives into the for loop, the variable index becomes left arrow to be the number 2, the first element of the looping vector. X bracket 2, left arrow, 3.6 times x bracket 1 times 1 minus x bracket 1. Runs out of code, index gets left arrow to be 3, the second element, x bracket 3, left arrow 3.6 times x bracket 2 times 1 minus x bracket 2. So, looks good. And now, I quickly define the first 5 elements. I could do this for maybe the first 200 elements. So I can very quickly define this sequence. And this sequence actually is really quite interesting in mathematics. It's called the logistic map. If you change this number right here from 3.6 to something else, the whole behavior of the series kind of changes. In fact, it displays some sort of chaotic behavior for values near where we are right here, 3.6. We can see it oscillating up and down, up and down, up and down, but it does some weird stuff every now and then. Like here, the magnitude of that oscillation kind of evens out, and it's a little bit smaller than before or afterwards. It's kind of a cool thing to study from a mathematical point of view. But hopefully a good review of for loops, that's going to be essentially our main engine of the Monte Carlo simulation, because we will just set up how many trials we want to have performed. We'll start at our value of counter at 0, and then in this for loop, we'll just set that up, and typically it's always going to look like this from I of 1 to n trials here, where we have code that performs the trial. We check to see if our event of interest occurred. If so, we bump up the value of counter by 1. So for most Monte Carlo simulations, our for loop is very simple. On the right-hand side of the in, we just have the integer sequence 1, 2, 3, all the way up to n trials, and the name of our looping variable, very often I'm going to take it to be I. I will equal 1, a trial is performed. We check to see if the thing happened. I will then equal to 2, the trial is performed. We check to see if the thing happened. If so, bump up counter. Then I equal to 3, third trial happens. I equal to 4, fourth trial happens. You get the idea. Within the for loop of our Monte Carlo simulation, we have the code that performs a trial. And part of that trial, we need to inject some randomness. We need to pick a random outcome, like heads versus tails, or picking a card from a deck, or picking what items a shopper has as they walk through a store. And one useful command that allows us to do this is the sample command. So if we have a finite set of outcomes, like head versus tails, spaghetti sauce versus bread versus lettuce, and we want to pick at random one or more of those outcomes, the sample command helps us to get there. So one thing that you'll spend a lot of time focusing in on when you do Monte Carlo simulations is this sample command. It allows us to inject that randomness and to sample from different outcomes. So the way that it works is that sample requires 4 different arguments. The first argument is just going to be referred to as x, and this is going to be our vector of possible outcomes. So if we're going to simulate a flip of a coin, our x vector might be heads versus tails. If we're picking a random color from an M&M pack, our x would be a vector of length 6, the 6 different colors we might get. If we're simulating the items that a grocery shopper picks as they're shopping, our vector might be pretty big, maybe 100,000 outcomes might be fitting inside that vector. So x is just the list of possible outcomes that we might observe, and size, the second argument here, lets us know how many we're picking. So if we're flipping a coin once, size equals to 1. If the shopper ends up picking 10 items, size would be equal to 10. We just need to know how many items from the elements of x we're drawing from. And then the third argument, just as important as size, is replace. Do we want to be picking with replacement or without replacement? With replacement means that we might end up picking the same element of x twice or more. If we wanted to flip a coin 10 times, we would sample from x being the vector heads and tails, size equal to 10, and replace equal to true. Because we're going to get multiple heads, we'll get multiple tails. If we were, say, drawing cards out of a deck, maybe x would just be the numbers 1 through 52 to represent the 52 cards in a deck. Size might be equal to 5 if we're drawing a poker hand, and replace would be equal to false because once a card has been dealt out, we're not going to be dealing it out again. We're not picking from those elements with replacement. And the last argument is optional, a prob argument that lets you give different probabilities to the outcomes that might be drawn. Now, if all of the elements of x are equally likely, like heads versus tails, you can omit this argument. By omitting prob, it's going to assume that each of the elements of x are equally likely to appear. But if you have reason to suspect that certain outcomes should be appearing more frequently than others, that's where you can put in your prob argument. So for each element of x, you'll have a prob vector, and the corresponding elements of prob will match up with the elements of x to give the relative frequencies. So let's just go through a few examples here. Letters is a built-in vector in R that gives you the 26 letters of the alphabet. So let's imagine that we wanted to generate a random word by picking 5 letters. Let's do 7 letters. Why not? Let's live a little. Let's pick 7 letters from this vector. So the first argument of sample is going to be the vector of outcomes that we're drawing from, essentially all the elements of letters here. I'm going to pick a word consisting of 7 letters. The next is how many elements do I want? I want 7 letters, so size equal to 10. And then I need to make a decision. Do I want the same letter to appear twice? Or once I've selected a letter, I can't select it again as I sample more? And true to the English language, we'll make sure to have replace equals to true because we might end up getting E twice or T twice. Now I'm going to omit prob. That way the frequencies of each of the letters that it's selecting are equal. A is equally likely to appear as Z in this word. Not very true to form with the English language, but once we run it, here's our example word. And it's kind of a long shot to generate a word from the English language for a couple of reasons. Number one, we know that the actual letter frequencies in the English language aren't equal. E's and A's vowels appear a lot more frequently, T's, S's. If you ever watch Wheel of Fortune, they always pick the same set of consonants and everything. So not very likely to generate an English word this way, but here we're picking these random elements from a list. If I wanted to flip a coin, say 20 coins, well, I could sample from the vector heads and tails. Size equals to 20 and replace equals to true. If I do that, I get a whole sequence of heads and tails. Or let's say that we wanted to draw 5 cards at random from a deck of cards. So what I'm going to do is to define a vector, actually, that represents a deck of cards. The cards with face values 2 through 10, then the jack, queen, king, and ace here. So I'm going to left arrow into deck a vector where I repeat the sequence 2 through 10, then add in a jack, queen, king, and ace. Notice if I just run that line of code right here, that gets me 2 through 10 and then the face cards. Notice that they're all characters. We can't mix and match characters and numbers in a vector. So they're all characters, that's fine. And I can simply repeat that vector a total of 4 times. So once I do this, I get a vector of length 52, and if I print out the contents of deck, that'll give me my deck of cards, 4 2s, 4 3s, 4 jacks, 4 aces, etc. So if I wanted to draw a poker hand, one thing I could do is sample from the elements in deck. So all 52 cards, equally likely to be picked here. Size equal 5, so we get a poker hand, and I just want to make sure to add in the replace equals false. Because if we're going to deal a poker hand, we don't get the same card twice. All 5 of those cards get dealt together. I don't need the prob argument because by default all the cards are equally likely. And so there's my poker hand. I got a pair. If I were to run it again, just kind of a random mishmash of cards. And so we can basically generate poker hand after poker hand. And we see that stuff like a full house, 3 of a kind, 4 of a kind, pretty rare. We didn't even see that. Now, what if we wanted to extend this simulation so that we took into account the suit of a card? If you get all cards of the same suit in poker, that's called a flush. And so in this case, what we need to do is be a bit more creative in how we're representing the deck. Because now there's 2 things that codify a card. The value that's being displayed, and then also the suit. The spades, the diamonds, the hearts, or the clubs. So what I'm going to do is to define a data frame, actually. And whenever I create a data frame, I tend to give it a name in all caps. My convention is that if it's a variable or a vector, it gets a lowercase name. Any 2-dimensional construct, like a matrix or a data frame, anything that looks kind of like what we'd see in a spreadsheet, that gets a capital name. And that's just my convention. You can do whatever you would like. And so what I would like to have is a data frame, once I spell that right. To set up a data frame, I need to give the columns names. So I'll go ahead and say, let's have one column be named value. And the values in that value column will just be the values of the cards. So whatever is stored in deck, that's good. And then I'm going to add a second column for suit. So is it a diamond? Is it a spade, heart, etc.? Now, the way that I've defined deck is that I go from 2 up through 10, jack, queen, king, ace. And so what I want to do is match those up with the appropriate suit. What I'm going to do is I'm going to repeat diamond a total of 13 times, repeat heart a total of 13 times. I'm going to move on to the next line. I'll repeat spade a total of 13 times, and I'll repeat club a total of 13 times. And then that way we guarantee that when we look at the twos in the deck, we get one of each different suit here. So if I were to print out the contents of deck to the screen and scroll up, I can see that the suits and the values are now defining the cards in their entirety. So how could I deal 5 cards from this deck? Well, in this case, what I'm doing is it's like I'm picking rows from this data frame at random. We're representing a card by 2 columns in a data frame, so let's just sample the rows of this data frame to represent picking cards at random from the deck. So if I'm going to draw 5 cards with values and suits from the deck, I can say sample, and in this case, the rows of the data frame are just row 1, 2, 3, all the way down to 52. I'm going to take 5, and we're going to have replace equals false. So if I sample the 1 through 52, these give me the cards, the rows essentially, that I'm picking. So what I can do is I can just put deck and then some square brackets and then extract out those rows. I want the 10th row, the 23rd row, etc. If I put some square brackets right after a data frame, put a comma right in between those square brackets, the value to the left tells me what rows I want, the value to the right tells me what columns I want. If I don't specify something on the left or to the right, then by default it takes all of them, so all columns in this case. And so here's my poker hand here, running it a few times. We're now getting a much more complete picture of what that poker hand looks like. I could check for straights, I could check for flushes, full houses, etc. Now, the last example that I want to look at is, what about that prob argument? So all the examples so far, all of the elements in that first argument of sample were equally likely to be picked. But sometimes that's not the case. If we're going to simulate opening a pack of M&Ms, the colors aren't equally likely. Some colors are more likely to see than others. So let's look at an example of the prob argument. And just for the sake of argument, let's sample at random with probabilities specified in a prob vector. And so what I'm going to do is I'm going to pick a number between 21 and 40. Let's say the integers 21 through 40. Let's pick 7 of them, and let's just try out different methods of doing this. So once again, if I were to just say sample 21:40, the values I'm interested in picking, size equals to 7, we'll do replace equals to true. If I leave off that prob argument, that means that all elements are equally likely. So they literally are just being picked at random, not in accordance with any sort of probability or weight distribution. So if I were to run that, well, here are the values that end up resulting. Now, it might be the case that I would like to give smaller values more weight than larger values. Smaller values are a bit more likely to be seen than larger values. So one way I can do this is to specify a vector prob, and you just put in the weights that you want each element of that first argument to appear. So if I were to say 20:1, we have 20 values that we can pick from. I've given it 20 different weights. It's essentially letting me know that the first element of what I'm sampling from, the number 21, is going to be 20 times more likely to be observed than that very last element. The ratio of these weights is 20, so getting a 21 would be 20 times more likely than getting a 40. And so this way, the larger the number is, the progressively smaller the weight that's assigned to it. And so if I were to run the sample, I should see it slightly skewed towards smaller values. Now, in this case, I'm still seeing a 38 near the top of the spectrum. That's randomness for you. But doing this a few times, we see that, well, maybe we're getting smaller values on average. I could take that to the extreme, actually. And if I were to square this vector, remember, whenever we do an arithmetic operation on a vector, that operation is applied to every element of that vector. So if I square this vector, 20 all the way down to 1, then that's just going to give me the squares of each of those elements. So 20 squared is 400, etc. And so now it is extremely likely to get smaller values, much progressively less likely to be getting larger values. There's just relative weights given to each one, each value we're sampling from. And so now we're seeing values that are fairly small. As I'm going through it, I'm not seeing any values that are much bigger than 30 whatsoever here. So if you want each of the elements that you're sampling from to occur with different frequencies, go ahead and specify that prob argument. Give each element that you're sampling from its own number here. The length of the vector given to prob has to be the same length as the first argument given to sample here. And just set up those weights as you see fit. If you had a probability distribution, like you should see 21 with a 5% chance, a 22 with a 1% chance, etc., you can put those in as your prob vector as well. But in general, that prob vector is pretty flexible. You can just put in relative weights. So the last thing that I want to talk about before getting into some more concrete examples is the set.seed command. And this is going to be important for doing any sort of scientific research. It'll be important for the homework, etc., because it will allow us to reproduce the randomness that we're injecting into our Monte Carlo simulations. You notice that every time I ran this line, I was getting a different set of numbers because it's sampling from these numbers just in different parts of the random number stream. So if I asked you on a homework, all right, generate 10 random values with the following weights, we're all going to get different answers. How am I going to know if you actually did that correct? And so all computer programs, all sorts of Monte Carlo simulations always are going to have this ability to essentially set up the random number stream to be in a very specific spot so that as random numbers are being generated, they are truly random, but the same set of random numbers will be generated whenever it's been set up in the exact same way. And so that's going to be the job of this set.seed argument. It's going to be all in lowercase with a dot in between there. And what we're going to do is to just put any number we want to. I like 533 for Bison 533. And that's going to allow you to essentially find a specific location in the random number stream. So that if you did a set seed 533 and then said, okay, well, let's sample these values, what's going to happen is that every time I run this line now, I'm going to get the same set of random numbers. And so that way, if you need to reproduce the results of your Monte Carlo simulation verbatim, if you've set that seed, well, it should get there. You can show to someone that, yes, the results are legitimate. If I'm asking you on a homework question, draw 10 cards at random from a deck with a starting seed of 1955, then we can all make sure to get the same set of cards emerging. Now, the one warning that I do have about the set seed is that last year R completely changed its random number generation process. And so depending on what version of R you have, sometimes set seed will give a different set of random numbers than someone else using the same seed if you're on different versions of R. It caused a lot of headaches in classes last year until we really tracked down. So that's why we always want to make sure that we're dealing with the most recent version of R. As of this recording, we're working on version 4.0.2, and as long as we're with that same version, whenever we set up the set.seed, we're guaranteed to get the same stream of random numbers that follow that. So set seed is going to be important for reproducibility. It's going to be important for turning in homeworks just to make sure that we converge to the same set of answers.